So today we are going to talk about SIFT, and this is a very important concepts and feature detector and the descriptor, which has really big impact on computer vision. So this is a detector and the descriptor also. We talk about Harris detector, which is like corner detector, but this is, in addition to detector, it is also a descriptor. It has two parts. So this was developed by David Lowe, who is a famous computer vision researcher. He is at UBC. He got his PhD at Stanford University. Then he was professor at NYU. And so this is the original paper, which has 25,000 citations and it's widely used. So SIFT is the key point extraction, and it stands for scale invariant feature transform. Okay, so it will not change if you change the scale, and it's actually patented by British Columbia, University of British Columbia. So if anybody use this in a commercial purpose, they have to pay the money to this university. And so it has some relationship to the human, visual system and cortex and so on. We're going to talk about that. So in a way, it's transform image into scale invariant coordinates. Okay, so goal is that we want to extract the distinct invariant features, as we did in Harris, which identify the interest point. But these are better because they are invariant. And once we can detect these features and descriptor, then we can match those from frame one image to other image. Okay. These are invariant to scale and rotation. If the image is rotated or a scale version, we can still do that. We'll give examples here. And they are, in general, robust to the affine transformation, which include the translation, rotation, scaling, shear, and all those things. And of course, change in 3D viewpoint. When you change the 3D viewpoint, then to the picture you get also, is different compared to from other viewpoint. And of course, it's not centered on noise and change illumination, all those things which you desire in a descriptor or detector. So the main advantages of SIFT are that it is a local feature. So therefore, it will be robust to occlusion, that if you have an object, if part of it is occluded, you can still find lots of other features which will be helpful. It's not a global feature, like a histogram is a global feature. So if there's a little occlusion, the whole feature will have problem. And it gives you a distinct points which you can match against large data set of objects, and it gets actually give you lots of points. It has quantities large, which is good, and you can have this real-time performance of this detector. So here's an example. There is an object car here, and the same object occurs in this clutter. There are some other objects also. Now these are the SIFT points, and then we have a descriptor around those points which are shown here, and these are the same points in this other image, which is a transformed version of the first image with lots of clutter, but we can easily match this point with this, which is this one, this point with this, which is this one, and so on. So that's a very interesting property of this. Okay, so now the main steps of the SIFT points extraction, which is similar to the Harris point extraction, are that we will build the scale space and we will select the peaks in the scale space. So this is scale space essentially is we will do this for different values of sigma, and we are going to go in detail. So a scale in a way is a sigma scale, the standard deviation of Gaussian, sigma 1, sigma 2, sigma 3, and so on. And in that we will find the peaks, and those will be the potential points or interest points or SIFT points. And then we will localize those and where exactly they occur, because we'll be hold a scale space. They can occur in different scales. And we will also assign the orientation to each of these points. This orientation will be like a descriptor. So some of you guys come late. Is a tradition? Why are you late? 10 minutes late? You have something else? Or it's fine? So you will come always late or just today? Okay, so please try to come on time, okay? Just respect. Assign orientation to key points and key point descriptor. So this descriptor is 128-dimensional vector, which is a feature vector, and that in a way actually is much more important than a detector. But we'll talk about both things. So let's go in detail what we mean by scales. Okay, so the scale in this context is what should be the sigma value when you apply a Gaussian filter, or Laplacian of Gaussian, or Caney. As you see that in the formula there's a sigma, a standard deviation, and we have just picked one and we apply it. So the question is what it should be. That's an important question, and that's a very old question. Okay, now one is well, let's apply multiple sigmas, and then you'll get, suppose in edge detector, Laplacian Gaussian edge detector, you can apply sigma 1, sigma 2, sigma 3, so you get multiple edge maps. Then the question is how do you come up with a one edge map, and the Moore-Hildreth criteria was what they call a spatial coincidence assumption. They say, well, if the edge occurs in several scales at the same location, then you say that's a good edge, and you declare that an edge. Okay, that was a long time ago when they came up with this Moore-Hildreth edge detector. So then there was a very interesting work done by Andrew Vidkun, and he's a computer scientist with a couple of other researchers are the only ones who have received the Oscar. Okay, and they did interesting work in graphics, computer graphics. So Andrew Vidkun did a BS from Columbia University in psychology, PhD at MIT, worked at SRI, worked at Schlumberger, and he was a professor at CMU for 10 years. Then he went to Pixar, and then unfortunately he passed away when he was doing scuba diving. And it was a big tragedy for computer science and his family and so on in 2010. But he contributed a lot to the computer vision, at the same time computer graphics, and actually he got a Moore Prize. As we talk about, Moore Prize is the most prestigious prize you can get in computer vision. And this paper is the 11th most cited paper in the computer science, whole computer science, and several other things, the deformable models, and Pixar gave him award, and lots of other things, SEM Computer Graphics Award, and then Oscar, and actually there's a credit for his work in the movie Cars too, and this is the location you can see if you are interested, and so all those things are good. So what he did, so he wrote a paper called Scalespace, 1983 International Joint Conference for AI. In the old days, the most prestigious conference for computer vision used to be AI conference, but now AI is not that popular, so there are more specialized conferences like computer vision, CVPR, ICCV, and so on. They are much more prestigious than HCAI. We don't publish in AI conference, he says. So this paper actually stories that first when he submitted the paper, it was rejected. Then he went to argue and it was accepted. Then he got a Best Paper Award, and it was a big revolution. Now there is the whole conference, based on Scalespace. There's books and so on. So the idea is very simple. What he says that what you do, you apply this Gaussian at different multiple scales, and then get the zero crossing, so which means you apply Laplacian Gaussian or second derivative Gaussian in one dimension and multiple sigma value, get the zero crossing, which are like your edges, and so that will give you something like a scale space. So let's say original signal is like this, and it's a one-dimensional, so just a row from one image. And then if you keep smoothing in different scales, it will look like that. So so this original, say sigma 1, sigma 2, and this will keep smoothing. That's what's going to happen. Okay. So now then you find the zero crossing and the second derivative of this, then you plot those. This is the sigma value and these are the zero crossing, so this becomes a scale space. Okay, and so this paper talks about that. It actually dealt with only one-dimensional case because it was interesting. So the idea is that you can take this scale space, which means you are applying the one-dimensional version of this Laplacian Gaussian many scales, 1, 2, 3, 4, 5, and all this. So it's like a continuum of scales. So I don't know why I keep doing this. So then what you can do is that you can take these contours. So these are the contours, which means at this scale there are this edge, this edge, this edge. These are all edges. But then when you increase the scale, this edge disappear, and then these two edges survive, and then they disappear. So because, as you know, when you keep smoothing, so there'll be more smoothing, there won't be any edges. So now you can take this kind of representation, come up with the interval tree, which is that they came up with that this is one interval, and then this will broken into 3 sub-intervals, and this will be broken further in that. So this is like a kind of flattening of this scale space, and that was one representation. You talk about that. And the way this is that you apply whole spectrum of scales, plot zero crossings, wise scales in scale space, and interpret the scale space contours. And these contours, as you see, they are open at the bottom and they are closed at the top, because there are more zero crossing at the lower scale than compared to the higher scale. So these zero crossing will disappear. And so this becomes interval tree, and each interval corresponds to a node in a tree. Then we have a parent and a descendant, and we have to look at that how much particular interval survives, and then criteria was that that you can identify those stability of each of the node by looking at or how many scales it really survives before it breaks into these other subinterval. Okay, so that is the top level description. You can come up with, given a one-dimensional signal, you can come up with top level description by iteratively removing the nodes which are not stable. Okay, and they are defined that if they are less stable than any one of their parents or offsprings, because every node has a parent and then offspring. So if they are not stable, compared to any one of those, then you remove those. So doing all that, at the end, what you come up with, that starting from here, this is your original signal. Then you can come up with a more stable description like that, because this may have a lot of noise, lots of things which may not be useful. And for this one, this is description. For this one, this is description. But this gives you a more stable description as compared to looking at the original signal. So that was the idea. Now, we are interested in images, so therefore we will look at the Laplacian of Gaussian. And what we will do, that we will look at the local maxima in this scale space of Laplacian Gaussian. So again, we have an image like this, and we apply Gaussian, and then we are going to, and these are the different Gaussians, and these Gaussians are these, filtered here. These are different Gaussians. There's a smaller one, larger one. You keep going like that. And so we want to, so this in a way is a scale space of an image. Okay, that scale space we talk about was a one-dimensional signal, and that's what we are going to use in the SIFT descriptor. Okay, so which means that we have a location in each of the image, and we have a scale. Suppose here scale be sigma square, and so on. So, so a scale has many different meanings, and you need to be careful when you talk about scale. One simple idea of a scale is the size. How big is a person in image? If the picture is taken close to you, then person may be large. Very far away, the person can be small. So that's a size or scale. Other notion of the scale is the sigma value in the Laplacian, Gaussian, and Gaussian filter, and so on. Okay, so here is a good example that we have two curves, and we want to say, well, what's the right scale we want to capture this information. So this is one possible scale, which is size of, in a way, Gaussian. Another scale. We have a range of scales, so which we don't know what's the right scale, okay, to capture the information which is there. So similarly, this is another curve, and we can look at these range of scales there. Now, question is, how do we know which one is the right scale? As you saw that Vidkun, gave another, one way to kind of not really select one scale, but come up with a description which is stable by finding these stable nodes in that tree. That was one way. Other way, here we are interested to say, well, what should be the right scale? What should be the right sigma value which we want to select? So it will turn out that what we can do, we can find the response at that point using different value of sigma, and we plot those, and these will be the responses. And it will turn out for this one, this is the right scale, and which is shown in the red circle. And for this one, and this is the right scale. And so that way we want to find wherever the response is maximum or the scales, and we are going to select that scale or that sigma value. And we are going to use this lots of different ways. Okay, so let's see what we will do in the two-dimensional case. So we have an image, and we have some transform version of in that image on the right side. So how do we find the corresponding size of the scale or the patches which are consistent, which we can match from one image to other image? Because these images are little transform version of each other, so we cannot use the same page size. That's not a problem. That will be a problem. So what we are going to do, again, we are going to apply this Laplacian of Gaussian and find the maxima where it occurs. So these are the different, as you see, we are changing the size of the window with the neighbor we are looking at, which correspondingly will change the sigma value, and we can plot these, and will turn out the maximum occur for this one here and for this one here. So in these images, even though we are looking at the same point, we have to use a different scale to make it meaningful. So that's the point. Okay, and so this is automatic selection of a scale by looking at the whole range of scales and finding the maxima of this response and selecting that scale. For this one, this is a scale. For this one, this is a scale. Okay, so that's one point. Now, so what that means that we can actually use the Laplacian of Gaussian as a blob detector. So these are the different Laplacian Gaussian. They're actually inverted Gaussian. As you remember, Laplacian Gaussian inverted Mexican head, so it's positive, it should be negative. So the idea is that we have these Mexican heads of different sizes. Okay, so now let's say we have an image. We apply this filter, and we look at the responses, and these responses are plotted like here. Okay, now if there's another image where we have a bigger size of blob, these responses are plotted here. Now these are responses. This is response for this sigma value, this is response for this sigma, and so on. So these are different scales. We apply this filter to this image, we get whatever response we put it. We apply this one, we plot these as we were doing before. So we get for this one like that. Another image, we have a bigger blob, and we get a response like that. And another one, we have an even bigger, we get a response like that. So as you see that we are going to pick the scale for each one will be where we have maximum. For this one, the scale will be this one, and for this one, the scale will be this one, and so on. Yeah.
Can you go into a little bit more detail? What is the maxima of
the Laplacian Gaussian? So you take an image, which image has, say, this blob, okay? And you apply the Laplacian Gaussian filter, as we talk about, like the edge detection. So you will look at, because you are finding this place, you are at the center of this, what is the value, what's the response, okay? Then you apply a second filter, which is shown here, and get a response. Then the third filter, so you'll have at least 4 different copies of the response of the original image, like that. Then you go through that and you plot the responses, and this plot will look like that, the first row, okay? So this is the scale 1, 2, 3, 4, 4, so something like that. So it will turn out that at this scale, it gives you a maximum response.
So maximum variance?
No, it's a response. You apply a mask and will give you some value output. So whatever the value is, that we are going to look at that value.
Okay.
You have a question?
Am I applying the filter on the whole image or just on...
Yeah, you will apply the whole image. I'll show you one example. Let's actually go to theater. Then we'll come back to that. Just 1 second. Just 1 second. So let's go look at that when we answer questions. Suppose this is the image, okay? So we apply sigma filter to this one. This is response, yes? And you apply another sigma. This is response. Now sigma is 2.5. We apply the whole image, okay? Then we apply the whole image, again 3.1, and all this. 4.8, 6.1, 7.6. We keep increasing the sigma, yes? So we get lots of these, 9.5, 11.9, and keep going. So now, so you have lots of these responses, you have these, and at each pixel you look at, go through these scales, images, wherever the maximum, because it will have values. You see here's value. There's a white here, there's a black here, there are values, yes? So each pixel, looking at all these images, you go through what is the maximum for that pixel along the scales. Yes?
So I look at all of my responses,
yes,
and I pick for each pixel the response that has the maximum.
Maximum. So you pick the whichever scale has the maximum, you pick that. Okay. And will turn out that this will be the output. So this circle show you the size of the scale. Okay? So suppose it happened that for this point, the larger scale had the maximum. For this point, the smaller scale has the maximum.
When you talk about point here, is that the center of?
Yeah, center of that. Yeah, because we are centering at each pixel. When we apply the filter, we center at each of the pixels. We apply like that.
Point actually on the edge, right?
No, okay, so let's not get into that right now. So we are just saying we are applying Laplacian Gaussian filter, and we are looking at the response wherever is maximum. Now, now you want to relate what he's asking, that we talk about Laplacian Gaussian filter, which was the edge detector. There we will look at where is a zero crossing. When the zero is an edge. So in this one we are not interested in zero. We are interested where is a maximum or extremum. Okay? So right now we are saying we have an image like this. We want to find out what is the right sigma value we should apply to each of the pixels. We are not going to apply the same sigma value for all the pixels. We want to determine that automatically. We want to solve that problem. How we do it? We take this image, we apply this sigma, we apply the whole image. We get this is a response. Yes? Then we keep doing that. We get lots of these responses, and then we go through these. Each pixel we have, say, about 10 scales. So from those 10 numbers we pick the maximum, and that is a scale for that pixel. We go to the next pixel, we look at those and pick the scale. That's a scale like that. So that is the output which is shown here, and the size of that scale is the radius of the circle. And it is exactly same as I told you in the one-dimensional case here, that what we are doing here, that in this case here, that we are looking at the response. This is a scales, different scales, and we are looking at the response of different sizes, and we pick, this is the maximum, we pick a scale. For this one was this one, and for this one is smaller one. So it's like that. Yeah.
How are the sigma being selected? I saw they're not.
Yeah, we're going to talk about that. You know, what is the best way to select and how many and so on. There's whole issues. Okay. Yeah.
What is the F in these graphs?
It's a response of the filter, response of the function.
The brightness of an
Yeah, exactly. Yeah, that one, like this one. It's not the brightness, but it's the output of the filter. When you apply the filter, so it's this one. So this is your original image, okay? So to this image you apply the filter, you get like this. Now at each pixel there's a value, and that is F. Yes? Okay.
So then at each pixel you're going to pick the filter that gives you the greatest value at that pixel.
That's right. I'm looking at all these filters. That's the idea. There was one other question. You got the answer? Huh? No? Okay? Okay, you're happy. You don't look happy. Okay, so that is right now, that's what we are doing. We take an image, we apply these filters, we apply many scales, and we look at the response at each pixel, we pick the one which is the maximum, and we take its corresponding scale. It's very simple. There's nothing hard about it. And that was, we were explaining here, that we have the, in same image or different images, we have different size of blobs. So if we want to detect this blob, then this will be the right scale, it will give you a high response. For this one, this will be the right scale, it will give you high response, and so on. So that's why it's also called a blob detector. This Laplacian Gaussian is also called blob detector. It will detect a blob. Okay, so we are looking at the maximum. So it's not an edge. Edge is a zero crossing, so that's very different. But even though we are doing this, applying the same filter. Any other question before I move on? Yes.
So in the butterfly image, like
Yeah.
the last one,
Yeah.
there are the number of circles are less, right, as compared to the number of pixels. So is it because like across all the cases, the other pixels have zero, like maximum?
No, I mean, maybe we just show only those, because otherwise if you show lots of them, it's very hard to see.
But like every pixel will have a maximum at least across all the...
Yeah, I mean, if there's it's all zeros, then there's nothing you don't have to do. But main thing is that you are applying to every pixel, and you are picking the one which is the maximum. So it may happen there's no maximum, then you don't show any circle. Okay, any other question? Okay, so this is a good step. So now what we are going to do, we will build up Scalespace. All the scales must be identified, scale invariant features. An efficient way to do this is the pyramid. Okay, and we discussed this before. And pyramid, as you know, you take an image, blur it, and then subsample, and that's the way you build a pyramid. And you're going to write a program to do that. And this is a pyramid here. And this is the same guy, Bird and Edison, that paper I mentioned to you. Now, the interesting thing is that the Laplacian of Gaussian, you can approximate by difference of Gaussian, okay, which is another very interesting result. So the idea is that, if you look at this equation, this is saying the derivative of g is a function of x, y, and sigma. derivative of g with respect to sigma is equal to Laplacian of this g multiplied by sigma. And this is called heat equation, and you might have learned in physics a long time ago. So it's heat equation. There are some phenomena satisfy this. Okay, so g is a function of three variables, x, y, sigma. So if we differentiate g with respect to sigma, then we find Laplacian of g with respect to x and y, and this is equal. If you take the Laplacian multiplied by sigma, they are equal. So what that means, that as we have learned, how do we find the derivative of Gaussian in a discrete domain? This is the first lecture. You just do the finite difference. You take the value of g at x, y, k sigma, for example, and subtract is x, y, sigma. K sigma is small distance in that sigma, and you find a difference, and then divide by this the delta, which is from k sigma to sigma, and that's a definition of derivative, finite different derivative. Okay, and this is equal to the Laplacian multiplied by the sigma. Okay, so we can simplify that, and we can bring this on this side, and then this will become, so we can take the sigma out, so it will become sigma minus 1 and sigma, and we have sigma from here, so we're going to sigma square and the Laplacian of g. Okay, so what that means, that Laplacian of Gaussian can be approximated by taking one Gaussian at sigma k sigma, another Gaussian at sigma. There are two different standard deviation of Gaussian. Subtract them, that is same as Laplacian Gaussian. So which is very interesting, and which really help us to do this very efficiently. And that's why the in the SIFT we are going to do in a way Laplacian Gaussian, but we are going to do it using difference of Gaussian. Okay, and there is also work in the primate vision that actually there are these cells which are doing the difference of Gaussian, because difference is a simpler operation as compared to second derivative in x, second derivative in y, and some type Laplacian will be harder operation. So that's the idea here. So the typical value of sigma is 1.6 and k is under root 2. So that's the values we are going to use in SIFT. So so now the first step in SIFT detector is that we are going to build a scale space, and this is scale space is for the image, even though the name Scalespace came from Vidkun's paper, which was just one dimension. And so we will take the original image and apply Gaussian filters to those at different sigma values, and we get these different filter version of the same image. And since this value, and this is your Gaussian filter, as you know, and the starting point k we will take under root 2, and then this is one level, and then we will do the subsampling and reduce the resolution half in x and half in y. It will be another level, and the way it's going to happen that that we will start with say sigma, and then next value will be k sigma. We'll filter with k sigma, then we will every time we'll multiply by k. So there will be k squared sigma, this will be k cubed sigma, and there will be k4 sigma. So sigma is fixed, but we will just keep adding, multiplying by k. K is under root 2. Okay, so these are filtering. We are filtering the image with different level of Gaussian blurring. Okay, so this here is different than this one, because this is k sigma, this is k squared sigma. There are two different sigma. We subtract, we get this, and that is the difference of Gaussian, which is the Laplacian of Gaussian. And we take these two, subtract, we get this one, we take these two, we take this one, we take these two, we take this one. So we'll get the range of these, of different sigma value of the difference of Gaussian. And that's the way we are going to do it. We could have done it, just apply Laplacian Gaussian filter, different sigma value, but they are doing this way, and which is more relevant to what humans are doing. So that's that, and then we'll start the next level, which will be start with a k squared sigma, and then again k cubed sigma and k4 sigma and so on. So we'll be like this. Now as you see that since the resolution here is half in x and y, so therefore this k squared sigma will have much more size as compared to k squared sigma at the bottom level, okay, because we have here the image size is reduced half in x and half in y. So impact here essentially, even though it just appear k squared sigma, but it is much more than k squared sigma at the first level, okay. So that is the way, otherwise there's no point to have this smoothing again, because we already did the k squared sigma. But here we are going to maintain the same sigma values, but we have reduced the image, okay. So therefore it will have twice as much impact in x and y as compared to applying at the lower level, okay, because if you apply say 5 by 5 mask in the higher level, it will become 10 by 10 at the lower level, because we are going to double in x, double in y. So that's the same idea here, okay. So once we get this, then we are going to again find a difference, because now let's apply one sigma value here, another sigma value, subtract, we get a difference of Gaussian, these two subtract Gaussian, and so on. And that is the scale space of the image at different sigma values. And that's what you are going to actually implement all this in the program. So then the question is, she was asking that, well, where do we start? That what should be the initial value, and so these are the different, so this level, each level is called octave, okay, it's related to music. And so, but every time given particular level or octave, then we are going to move it by under root 2 sigma. So starting here, then we'll get this, multiply by under root 2 sigma, under root 2, we'll get this, keep going like that. If you start with this one, again the next one will be we multiply by under root 2 like that. And these are the different value of sigma as you saw here. That's what we have. So every time we are multiplying by under root 2, k is under root 2. So that's the way we are going to build that. So for this SIFT, the starting point sigma is 0.707187 and k is under root 2. Okay, so that is how we build the scale space. Now the first question is, how many scales should be in each band? Because as you saw here, we did 4 or 5 of those, but can you do 6, 7, or why you stop, then you subsample, you go to the next one. So that's the question. So so now this point was determined empirically. What Lowe did, he took several images from range of different domains, and there were outdoors images, human faces, aerial photographs, and so on, and then took those images, applied some transformations, like rotation, scaling, and some fine other transformation. So you have transformed versions of these images. And then he did the study that, well, let's pick particular number, let's say if we have only one scale, then what's the performance? If we have 2 scales, 3 scales, so these experiments give you that what will be the performance, and he picked the one which give you the optimal performance. Now, how do we measure the performance? So one is that you have an original image and you transform. Suppose you rotate it. And you know, because these images are known, you already know the ground truth. So you take an image and transform, you rotate it, you get second image. Now you know a particular point here, and you want to be able to find that point in this rotated image, okay? So you say, well, go through this whole process. Well, if I use only one scale, how will I be able to find? If I use 2 scales, will I be able to find 3 scale up to 8 scale? And he did this for all these images. There are lots of images. So then found the average, and he said that, well, this is called repeatability, that if you use only 2 scales, or one scale, the repeatability is not good, because repeatable means you are able to find it. So repeatability is less than 80% if you just use 1 scale. But if you use 2 scales, then it goes up, and 3 scales, it goes up, then after that it goes down. So that was the one measure to say, well, I have these images, I have their transform version of images, I go through number of points, and I want to find the exact point in the rotated version and say how many of these I can find while using 2 scales, how many of them you can find 3 scales, 4 scales, so on. And he found out that for that, 3 scales was optimal. Less than 3 is not good, but more than 3, it doesn't make much difference. And that was the criteria I decided to do 3 scales. Another criteria was that, well, if you get a point in image and then you want to match that point in the rotated version of the image, and if the descriptor can match with that, then we're going to talk about descriptor. But that was another curve which is shown here, the second curve, and that also confirms that 3 scales is a good optimal choice. If you use less than that, the repeatability is not that good. If you get more, it doesn't make much difference. So that value of number of scales were determined by empirically, by doing the experiments, okay? Because that's what we want to do, that we expect the images to appear in different rotation, different scale, different illumination, different noise. He simulated all those, and it was a very extensive study, and he found out that we can determine these, and that's pretty much what they did. So that is how many number of scales per octave per level, okay? So then second question is, what should be initial value of sigma? Again, he did a similar experiment, and these are the curves, and found out that 1.6 is kind of the right value, because after that it doesn't make that much difference. But if you use the more, then you have more computation. Remember that if you increase the sigma, you have bigger mass, and you'll be in lots of multiplication. So that's why that was a compromise in 1.6, what he did. So now, given an image, you can compute this scale space, which essentially apply the different Gaussian of different scales, and then subtract, and then go to the next level, again apply the Gaussian and subtract, you get difference of Gaussian. So that's the scale space for the SIFT detection. So in that, the idea is that now suppose you have these 3 levels, okay, and at each level you have some value. Now you want to determine if that particular pixel should be declared as an interest point or not. And the way he was doing that, he's going to look at the 3 by 3 neighborhood at that scale, 3 by 3 neighborhood above that scale, and 3 by 3 neighborhood below that scale. So total there are 26 neighborhoods, okay? 8 in that semi-scale, because the 9th one is the one we are looking at. 9 above, 9 below, so 26 neighbors. So if this particular pixel is larger or smaller than all those 26, then that is the SIFT point, that's the interest point. Okay? So that is the criteria, which is very simple. And so that will give you large number of the extrema. So these are minima or maximum, so that's called extrema. Okay? And now this will give you lots of them, because there will be many of these points which will be extrema in these 26 neighboring values. So then we want to refine these initial peaks. These are basically peaks, whether it's positive or negative peaks. Okay? Yeah.
I just wanted to clarify, when you're talking about these three images, those are within one level of the pyramid,
Yeah,
right?
yeah. Within one level of pyramid, yeah. So
the
we got,
differences of...
yeah. I mean, so this will be, what?
Yeah, I wasn't understanding. Is that the octave you mean?
Yeah. Level octave is same thing. So you can look at, this, they are different scale. So you have given a scale, and you are looking at the scale above and below, and you, of course, cannot look at the bottom one because there's no below, and you cannot look at the top one. You cannot do that. But from going from one octave to other octave, the transition is fine, because these scales are changing. And so we can even, in principle, we can look at across the octave also, because it is in continuum of scales. Okay. So so that's what we are going to do. So the candidates are chosen from extrema detection, and suppose this is the original image, and these are the extrema location. These are either maxima or minima in that 26 neighbors of that particular pixel, and they are shown here. There are lots of them. Okay. And so now there'll be some which will be outliers, which we want to reject. Okay. And they can be due to low contrast, and they will be poorly localized candidates along the edge. And to reject the outliers, we are going to use the Taylor series. Remember, we talked about Taylor series before, and this is another application of Taylor series. So what we have, this range, the output we have many these images, difference of Gaussian images, and we have x, y in each, and then we have sigma. So this is a three-dimensional function. So this is x, y, sigma. Okay. So that function is d, x, there's a vector which is x, y, sigma, and we are going to do the Taylor series of that. So the value of that d at a given point, we want to expand the first derivative of d. Now this is the the vector value function, so we are going to differentiate that and x, and then the second derivative of d. So this will be a Taylor series, because this function of 3 dimension. So we'll have to have this kind of thing. So we'll not only find the derivative with respect to x, but y, but sigma, and similarly second derivative with respect to x, y, sigma, and so on. So given that, what we want to do, that we want to locate where exactly these maxima occur, which means during the Taylor series expansion, we are going to locate these, and this will be a part of the homework, that if you differentiate this Taylor series expansion and then equate to 0, you will find the maximum of this will be given by that, and at that location we are going to apply a threshold. If at that extrema location, if the value of this difference of Gaussian is above some threshold, then that is a genuine interest point. So this will be on the top of it, that it has to be extrema almost 26 neighbors. But now we are to localize exactly where this occurs, because this will give you a more continuous version of where it occurs. So that way we will be able to remove some of these outliers. So One on the left is shown the original ones. So we have 832, and when we apply this threshold, we get 729. So that improves that some of these are rejected. So the process, this step again is simple, that we are going to find the exact location where the maxima occurs, because here what we were doing before, that we just have the integer value pixel. Now extrema can occur anywhere in between pixels, because this is a discrete, so there's a problem there. So we want to find out exactly where the location is in sub-pixel accuracy, and that we can find out by Taylor series expansion, and this location x hat will be given by that, and we will find what's the value of the x hat. If that value is above some threshold, it can be minima, maxima, but it may be very small, so we don't want to take that. So it has to be above some threshold, and we'll pick that. And that way, we are going to get some improvement. So that is the first step of after finding these candidate locations which are shown in the. So we can do better, and in particular, along the edges, as we have talked about, Laplacian Gaussian is actually edge detector, and will give you zero crossing at the edges. But we are not interested in edges now. We are interested in interest points. So we may get some of these candidates which will be edges. We want to remove those. And here we will look at the surface. If this difference of Gaussian, that function, we are looking at dx, y, sigma. It's a surface. Then we want to look at the curvature of that surface, and there are these two principal curvatures, and the poorly defined interest points will have low curvature in one direction and high curvature in other direction. Okay, so low curvature in particular on the edges, because edge is nothing going to change along the edge. So we are going to identify those, and the way we are going to do is we are going to look at the Hessian matrix of D, which will capture the principal curvature, and that will be like this: dxx and dxy and dxy and dyy. Now, since you have the D, which is the function of xy sigma, here we're just looking at the spatially how it changes, not around the scale like sigma. Then we can apply finite difference, anything you can find a derivative, as we have talked about, first derivative, second derivative. So you can compute these terms at each of the location. So once you have that, then ideally we want to look at the eigenvalues of this, as we did in the Harris detector. But we can do simpler way that we look at the trace of this matrix, which is the summation of diagonal element, and the determinant of this matrix, which is given here, this multiplied by this minus this multiplied by that. As we have talked about, the trace is sum of eigenvalues of this matrix. The determinant is product of these eigenvalues. Okay, so you can directly, looking at a trace and determinant, you can find the ratio of eigenvalues compared to actually evaluating, computing the eigenvalues eigenvector. So what we are going to do, we are going to look at the ratio of these two eigenvalues. These are the eigenvalues on these principal axes. So this ratio is lambda 1 upon lambda 2, and then we want to use that without actually computing the eigenvalues, and using the property of a trace. So if you take the trace squared divided by determinant, then this is a definition of trace, summation, square, and product of eigenvalues. We simplify, you come up with this expression, where R is a ratio of these two eigenvalues, lambda 1 divided by lambda 2. Okay, so therefore we are going to use this ratio of trace squared divided by determinant, which will give us some idea about the ratio of these two eigenvalues. So at the end, what will happen that we will say that when R is 1, then these eigenvalues are same because there's a ratio. Okay, and it will increase when with R. So we want to eliminate the points, key points, if R is greater than 10. Okay, so therefore on one direction the curvature is very high and other one is very low. So that we want to avoid, and those are mostly the edges. In one is low and on this one high. So then bottom line will be we get this matrix and add the diagonal element and product find the determinant and find this trace, multiply by trace square divided by determinant square, and we say that if this is less than this, where R is 10, then we'll remove those points. So that's the whole process. So what is happening, that what we are doing is based on some scientific concepts. We can just do ad hoc things. Well, let's compute something, apply threshold 10, 11. But here we are saying, well, we want to remove those outliers which are along the edge. Now, how do we know? We say, well, we look at a surface which is computed using this difference of Gaussian, and the edges will be along the edges. There will be curvature will be very small, and across will be high. So now, how do we find out how much is the curvature? We can take that matrix, find eigenvalues and all this thing, but we say, well, we don't want to do it. We just want to simply just take a matrix which is shown here. We find these, add up these values, and then find the determinant of that, which is very easy. Then look at the ratio of these eigenvalues, and from there we can derive this idea of that we can actually get this ratio equal to in terms of these lambda 1, lambda 2, then apply a threshold on that. So that's kind of the process, and it works. Okay, so if you do all that, then this is what we are going to get. So from 729 points, you can get 536. So you're getting rid of a couple of 100 points from this thing. So then the next thing is that we have now localized the interest point, and we have removed the outliers, and we want to now find out what is the orientation of that interest point, the dominating orientation of that interest point. Because as you know, we are looking at a point, we are looking at a small neighborhood. Each pixel in the neighborhood has orientation, because we are computing gradient direction, there's some orientation. So we want to say what's the most dominating orientation, and that we will assign to that interest point. So, and it's important that we will have the rotation invariance. Even the image is rotated, then since we are normalizing with respect to the dominating orientation, we will, will not have a problem. So what we are going to do is take this D or L, which is difference of Gaussian or Laplacian of Gaussian, whichever you call it. We'll compute the gradient of that, the magnitude and the direction, and then we will create a weighted histogram in a small neighborhood of that key point. So let's say we take this small neighborhood. Each of the point around that has a gradient direction, which are shown here. Okay, and then we will have the 36 bin histogram. So there are 360 degrees angle. So we'll divide in 36 every 10 increment. So the count, how many are there when the angle is 10, how many are there when the angle 50, and so on. And then we can apply weights to those bins, those counts. If the particular direction magnitude is high, so here is showing direction, and the length of this vector is the actually magnitude. So this is much more important than this one, it's a small magnitude. So you can apply to each one weight which is proportional length of this vector, which is the magnitude. So that's what saying gradient magnitude weights. And also we can have the weights according to Gaussian, that the central pixel will have a higher weight, the pixel which are away from it will have, smaller weight. So using these weights and using at each pixel in the neighborhood, getting the gradient direction, we will come up with the 36-bin histogram, which will show us that how these gradient directions are distributed. And you wrote up already a program in the first assignment. You can take an image, you can find the gradient direction, gradient magnitude, and then this is obvious that you can quantize those directions in 36-bin, and you can find histogram. You just count. So it's pretty easy. Okay, so that's what we are going to do. So now suppose for this one, this can become a histogram showing that we have a lot of pixel in this direction, few in this pixel direction, and so on. This is showing not all 36 bins, but this is just illustration. So this is kind of histogram, even though histogram will be one dimension. This is illustration of that. So then in this histogram, whichever has the highest number, whichever bin, histogram always have bins, okay, it will have 36 bins. In each bin we are going to count how many pixels have this orientation, how many pixels have this orientation, and so on. So we will look at the histogram, whichever has a maximum votes, maximum number, that is the orientation of this interest point. Because in that neighborhood, most of the pixels are in that direction, gradient direction. So that is the way we are going to determine the orientation of that interest point. Now it can happen that for some interest point there are two peaks which are very close, then that's a problem because there's no unique peak. So if that is the case, then we are going to introduce one more peak around for that interest point. It is a peak which is the highest, but which is the next highest also. So that way it will give you much more information as compared to ignoring just looking at the highest peak. Okay? And if that second highest is within 80% of the first highest, we are going to introduce, more another peak in that direction, with a different direction, with whichever the peak is. Okay, so that's the orientation of interest point. So we know the location, we know the orientation, we know how to remove outliers and all this. That's the whole process. Okay, so now we want to come up with the descriptor. That what should be the descriptor around that neighborhood, and that is called SIFT descriptor. So far we have talked about SIFT detector. There are many steps in that. And as I told you, that the bottom line is that at the end, what is useful is actually descriptor, which is very easy to understand. The detector has lots of steps, and it's not that different from Harris. You can use just Harris detector and SIFT descriptor. Okay. Now, so SIFT descriptor. Now the question is that what should be the descriptor around a small interest point? So possible descriptor can be, we can just look at the small neighborhood and get some intensity values of that around that of that image. But intensity values will be sensitive to noise, lighting, and so on. They're not stable. Okay. So what we are going to do, we will use again the gradient orientation histograms as we use for finding dominating orientation. We'll use this again for finding a descriptor, and you will find out, we'll going to talk about next one called HOG. There also we are going to use orientation. So orientation of the gradient is very important feature which will be very useful. Okay, so so this will be a robust representation, and so it's again related to our cortex of the humans and different animals, because there are the neurons which are respond or tune to particular orientation. When a human see, particular, direction, then they will fire. And that's the way the brain works and so on. Yeah.
So is this all in the eye or in the brain?
Yeah, so eye, there's a retina, there's a cortex, there's a whole thing. So they start with the retina. Retina has these different things, and then I think they even talk about the cortex. So there are different, levels of that, and it's become very complicated.
But that's even before it gets to the brain, the signal.
Yeah, this whole thing is brain. Isn't it? After eye, it's retina is part of the brain, right? Retina, and then all these things. So I don't know much about, but that's what it is. This whole thing is a brain, including eyes is a part of brain. Okay, so what they found out that these neurons will work even though you shift the location of the response. They will respond if there's orientation like this. If it's here or if it is below here, it will respond. So location can shift and it will be still okay. And the paper he's citing is Tommy Poggio from MIT, and I showed you the picture with David Moore. He was his postdoc when Moore started at MIT. And he's still working in that, and they have a nice paper, 1997, and they found out these cells, and these cells allow for matching and recognition of 3D objects from range of viewpoints. You show one 3D object, and you rotate, translate, and another one, then still they are able to find. And these are the experiments they did. But these are the neurophysiologists, that do that. Experiments show better recognition accuracy for 3D objects rather than depth up to 20 degrees. It's rotated, 20 degrees still work. Okay, so now how we are going to find these descriptor? So what we are going to do that we are going to look at the 16 by 16 neighborhood around that interest points, and we will compute the orientation magnitude. Then we will generate the weighted histogram, very similar to when we are finding the orientation of interest point. And here now we'll have 8 bin instead of 36 bin there. And we'll divide 16 by 16 into 4 by 4 regions. So we will have 16 regions. And for each of the region, we will have this histogram, which will have the 8 bins. So we'll have 16 histogram. Each histogram will be 8. So 8 times 16, 128. That will be a descriptor, which is called SIFT descriptor. Okay. So here's example. Now instead of 16 by 16 here, we are taking 8 by 8. So we divide this into 2 by 2 regions or windows, sub-windows. So we have 4 sub-windows. For each one we get the 8-dimensional histogram, which is shown here. These are different orientation, different bins. So, but in particular we'll have 16 of those, and each one will give you 8. Then you concatenate all this 128-dimensional feature vector, which is a descriptor. Okay? Now we are not done yet, so just wait. So we are going to normalize this. So the first question is that how big these windows should be. So again, he did the empirical experiment, looking at these images and transform version of that, and looking at different orientations with whether the histogram should be 4 bins or 8 bins or 16 bins. So these are the different curves for these different bins, and this axis show you the width of that sub-region. So and this shows you the correct nearest descriptor that you get original one, you get all this, and you go to the transform version. If you can match correctly, then that's good. So here, as you see the results, number one is that that the the after 4, then it's flattened out. And other thing you will notice that for the 8 orientation, which is this one, that give you better than the 4 orientation, which is this one, and or the 16 orientation, which is this one. So that's why selection is the 4 regions and 8 orientation, and that's what we did here, as you see, 4x4 region and 8 pin. So that's that, and then we will take those numbers, 128 numbers, put in a vector, and we will normalize that vector by taking the magnitude, divide each element, unit vector, okay? And that will help us to get rid of elimination and variance and so on. Then we'll do one more thing, that we will find out the each element after normalization. If it is more than 0.2, then we'll make them 0, and then we will normalize again. So that he found out to be helpful in getting rid of these nonlinear intensity transformation and so on. Okay, so so that's it. So we are done with the descriptor, and it's a simple idea. It's not that bad. Take interest point around a 16 by 16 neighborhood, divide that 16 by 16 region of 16 4x4 regions. Each 4x4 get a 8-dimensional histogram orientation weighted by gradient magnitude, put in one long vector, 128 dimension, do the normalization unit vector, get the numbers which are more than 0.2, make them 0, normalize again. Okay? So now the reason we want to do all that is we want to be able to match the images. We want to take a point here in one image and match it the corresponding point in the next image, and that image is rotated, translated, and there are lots of changes to that. That's the ultimate goal. Yeah.
Why would we get rid of the ones that are greater than 0.2? Those will seem like they would be the biggest magnitudes in the vector. So dominant edges.
Yeah. So I mean, that may be due to some some transformations. Some maybe particular pixel may become very bright, or some due to that. So we don't want to kind of rely on that one pixel, which will impact all of the 16 by 16 neighborhoods. So we want to remove that and rely on the most of those many more pixels, and because otherwise if they be so high, then other will have not much impact. So that's kind of motivation.
So we kind of take out the most biggest. Okay.
Yeah, I mean, so see it's like outliers. When you any distribution you have, the outliers will create a lot of problems, right? If you have outlier, one very high number, one very low number, then this whole distribution will have a problem. If you want to match those, just find the mean of the distribution, then outlier will just give you completely wrong information. So that's why these very high number or very low numbers, in general, they are not that useful. So you want to look at the overall what is there, because then one particular pixel can be due to all the noise, some other reasons. So that's why he's removing that, and it works better. Okay. So now we want to do, yes?
I don't understand why is this particular thing invariant to rotation. For example, you have a image and you take a small amount of it.
Yeah.
You calculate the HOG.
You
say you get a direction in one particular thing. Now the same part in the other image, because it's rotated, point in some other direction.
Yeah, because see that's a good question. So see that these orientations are with respect to with respect to one particular angle. They are not absolute angles. So see, as we say here, don't know where was that. Maybe okay. So what we are going to do, this was about the so we are going to do, this is what I was looking for. So this orientation is relative. See, so if you are looking at the particular pixel, the key point, now we look at the other non-rotating pixel with respect to that. So that will not change even you rotate the object, because that particular is also rotating. So it's a relative. It's not absolute with the x-axis or y-axis. So that's the reason it is invariant. That's one reason. Other reason is in general the histogram is invariant because to this transformation, because you're counting, how many pixel have this particular orientation, but any other descriptor will not be. Distribution is always invariant to lots of things. So this is also the reason that you are dividing, and these neighborhoods are so small. So one possibility will be, say, well, take the 16 by 16, get one histogram. But the reason we are doing that, they are very local, and that will be less sensitive to these transformations, and that's what we found out. Okay, but the main reason is because of relative. So it will not make a difference. Any other question? Okay, so let's see where we were. Yeah, okay, so we are here. Now, so we have a descriptor, we have a point, we have a descriptor, and we want to match that. Now, what's going to happen, say we have a database, we have many images, and each image has many interest points, and each interest point has a descriptor, as we have been talking about. So we have a big database. Now we have an image, we find the interest point. For each interest point, we get that descriptor. Now, given that descriptor, we want to go through all these, find the best match. And we return next interest point, get a descriptor, find the best match. So that's the way we are going to do. And so the obvious way will be that, well, when you find the best match will be, we have a 120-dimensional feature vector, and we have lots of these feature vector, 120-dimensional, we just find Euclidean distance. If it is exactly same, the Euclidean distance will be 0. That's the nearest neighbor. Maybe it's not exactly same, it will be small number as compared to other ones. So we are going to compute that. Okay? So it's called nearest neighbor. So we find the input image, we have a vector, 120-dimensional SIFT descriptor. We have lots of other descriptor for the database images. We find the match, and we find the distance. And whichever give you a small distance, that's a match, and that is called nearest neighbor, the first nearest neighbor. There can be next nearest, second nearest neighbor, third nearest neighbor, and so on. So, what they do that may happen that the first nearest neighbor and second nearest neighbor are very close match, and that can become a problem because it's ambiguity. Let's say the distance from the input image descriptor to the second nearest neighbor is 1, and the first nearest neighbor is 0.8. So they're very close, and it's ambiguity, and we don't know whether first is better or second is better. So he came up with this idea that we want to select the match if the first nearest neighbor is less than 0.8 distance from the correct match compared to the second nearest neighbor, that there's a big distinction. So clearly a winner. So that's the main idea. And so to explain that better, so you have two images. They are little transform version of these images, and these are little neighborhoods we are looking at, different scales, and we'll get a descriptor in each of those. So the question is, given this, we want to find out what's its best match. It's a very complicated thing because there are so many of those. So we have a descriptor and we want to find out most similar appearance of SIFT descriptor, and we'll find the closest one. And so to explain this further, so this is input image and these are the interest points which are shown here. Now for this particular interest points, this is the first nearest neighbor, and this is the second nearest neighbor, and this is the third one, and this is the fourth one. So now some of them are correct, but some other ones are wrong, because and we don't know. We have all these things. We don't know. We have select one. So what we are going to do, to correct, to detect the right match, we are going to look at the distance between the input descriptor and the first nearest neighbor. We are looking at the distance and we are going to look at the distance between input and the second nearest neighbor, and we will find the ratio of that. And if this ratio is less than 0.8, then this first nearest neighbor is the good match. If the ratio is not less than 0.8, then it's ambiguous and we are not going to select that. So that's the idea of this. So what we are going to do is, so we will find a distance, which is Euclidean distance from the input descriptor to the base match, which is 128 dimensional feature vector, and we'll find the distance pixel element by element, and we'll find the distance to the second match and look at the ratio. If it's less than 0.8, which means the distance to the first match is less than 0.8 times the distance to the second match. It's a smaller distance for the first match very clearly compared to second match. So that's the idea, and that will give you better. Yes.
The distance is only from the single descriptor, or is it
single
image?
No, single descriptor. So see what we are going to do. We will do this thing for all of these. So for each of the point in the input, we'll find out what's the best match. For the next one, what's the best match? What's the best match? So ultimately, what's going to happen that each of the match will give a vote. So suppose 15 points match to somewhere in this image. 2 points match to here. 10 points match to here. So we say majority of points from this input image match to this image, we'll say that's a match. So because we are starting with the local matches, then one way to go to the global match, which is the image match, we'll just take the votes, and there are many other methods. Okay? So right now we are just talking about how best to match a point and its descriptor to a point and other image. Okay, yes?
Does this point A come from a student?
No. So you will again, you have an image, you apply your SIFT detector, you will get these points.
No, I mean the point A, the number.
0.8, yeah. This is from I'll show you the graph. I mean, he again did the empirical thing. Okay, so that's a good question. Okay, so let's look at that. So this, this thing, what's the best match, and we look at the distance ratio and 0.8. If the high could be ambiguous. So this is what answer your question. So he did again experiment and look at the ratio, different values of ratio as shown here, 0.1, 0.2 up to 1. Then find out the distribution of these correct matches. So this is a curve for the correct matches. As you see, if you use ratio 0.2, you have this many correct matches. 0.3, you have this many. 0.5, this many. So these are all correct matches because you know the ground truth you can match. So this is a distribution. Now this is the curve for the incorrect matches. So for the 0.3, incorrect matches, small, small, small. Now if it goes higher than 0.8, then it jumps up. So that 0.8 is the good compromise, that you maximize the correct matches and minimize the wrong matches. That's what he found out. Okay? It's good? Yeah, okay. Okay, so that's the result. So the summary is SIFT detector generate a scale space of an image, detect peaks in the scale space, which are extrema, localize interest points using Taylor series, remove outliers, remove response along edges using that Hessian, assign orientation, and SIFT descriptor compute relative orientation. Again, look at the relative word as you asked earlier. Relative orientation magnitude in the 16 by 16 neighborhood, form weighted histogram 8 bin for 4 by 4 regions, and then get the 128 dimensional feature vectors of the descriptor. And this is the paper to look for, as you say. So one of the most cited paper in computer vision. Okay, so this is again a very popular descriptor, and this is called histogram of oriented gradients, and it's called HOG. It's HOG, HOG. And this is a paper. It has close to 9,000 citations, and these are the authors. HOG, histogram of gradient orientation. Again, very, very useful thing. It's used in lots of places. It's very, very important. So this is again a descriptor, like SIFT descriptor. This is descriptor, and it is relying on the gradient orientation. And so you compute the gradient, as we have been doing, and then you have gradient orientation magnitude, and if you have color images, you know we have 3 channels, so you can pick one of the one which is the highest magnitude and just find the HOG for one channel. And originally this was designed for detecting humans in an image, and so there the standard size is 64 by 128 image, and we want to come up with a descriptor for that. Like SIFT descriptor was for 16 by 16, but this is a bigger one. And we are going to divide this image into 16 by 16 blocks with a 50% overlap. I'll show you how. And with that we will have about 105 blocks in total for this whole image. And for each block will consist of 2 by 2 cells, and where each block will be 8 by 8. So then we'll take the gradient orientation and quantize in 9 bins. Okay, remember in the SIFT is quantized in 8 bins. Here 9 bins. Then the votes will depend on gradient magnitude, very similar to the SIFT. And then we can interpolate if the gradient orientation between. I'll show you how. And then after that we can apply another Gaussian to smooth it out. And then concatenate all these histograms to a very big descriptor, 3,780 dimension. So you have 105 of these blocks. Each block has 4 cells, and each cell has 9 dimensional histogram. So you multiply 105, multiply by 4 by 9, 3,780. Okay, so this is standard thing. So you'll find the derivative, center difference. When these are the mask, gradient magnitude, orientation. We have done this many times. So let's look at this as an image, 164 by 128 by 64, and these are the 8 by 8 cells, and then we'll take the 2 by 2, 4 cells in one block. It's block 1. Then another block will be like that, 50% overlap. Okay, so like that you will have 7 of those in this one. 1, 2, 3, 4, 5, 6, and the last one will be 7 here. And in this one you will have 15. So that will give you 7 times 15 is 105 blocks in total. Each block should be 2 by 2 of cell size 8 by 8. Now, so we'll quantize these directions in 9 bins shown here. And so these are the counts. Suppose if it's 85, then 1/4 will go to 70 and 3/4 will go to 90. It's like interpolation. And what is a gradient magnitude? Interpolate as an example, so if theta is 85, so which bin you should put? So you will say how close is 70, how close is 90, and then you take those appropriate weights, 5/20 and 15/20. So this gets 1/4 and this gets 3/4. So you can weight the votes also based on the Gaussian. So final feature vector for this whole image will be this concatenation of these histograms. So if this is an image, now we will have these histograms, each of those, like here, and each of this block. And as you see that when you look at this representation, then you can see a person, is that right? So these are like arms of person, the orientation, this thing. There's nothing, it's a background constant, so it's 0 or 180. So again, this person, has these arms here, so these orientations like that. And this is the like a body of person. So there's nothing here. So you can visualize these. It looks like a person, yeah.
What is the input for the weights? Is it color? You said it color, or is it just the rate of change?
No, the weight is the gradient magnitude. So if you have a color image, just pick one of the channel, treat it as a black and white, and compute a gradient magnitude, and all this thing. So when you will find the histogram, so you for each of the orientation you quantize into these 9 bins, okay, which is shown here. Then the vote is a gradient magnitude. It's exactly same as we did before in the SIFT. So if the gradient magnitude is large, then you get more votes as compared. You can normalize it. Say, well, maximum is 1 vote, and then depending on 0.7 is 0.7 vote or something like that. So it will be proportional to gradient magnitude, and the histogram is of the direction. So that's what we are going to do. Okay, so that's it. Comparison between SIFT descriptor and HOG. Yes. So SIFT is 128-dimensional feature vector. It is looking at 16 by 16 window, and then that window is divided 4 by 4, and there are total 16 of those sub windows, and each one has 8-pin histogram, and HOG is 3780 dimensional vector. It is looking at 64 by 128 window, and dividing that 16 by 16 blocks with overlap. Each block consists of 2 by 2 cells, which is of 8 by 8 size, and this overlapping, and then 9 histograms. So it's comparison between these two descriptors. So at the end, they are doing very similar things. So many people have started using just one of the histogram, looking at your 16 by 16 window as you look at 16 by 16 window in the SIFT. You don't have to look at the whole image, 128 by 64, and get this 3000 dimensional feature vector. So the one big motivation is that SIFT is patented. So if anybody wants to use SIFT for commercial purposes, you have to pay royalty to University of British Columbia. HOG is not patented. So these companies, they will actually use HOG instead of SIFT. So to answer your question, it doesn't have to be that size. You can take it just 16 by 16, do that, and just get one histogram. And that's mostly big use of hog is like that. And there are different variations. Okay.